In this video, we're going to discuss Kepler's laws of planetary motion. Now, Kepler's first law of planetary motion states that the planets orbit the Sun in elliptical orbits, with the Sun located at one focus of the elliptical orbit. We can see here the Sun located at this point, which represents the focus of the ellipse. This X represents the other focus, and we can see that there is empty space where the other focus is located. This elliptical orbit is that of this particular planet, and the direction of motion is given by the arrow. Now, Kepler's second law of planetary motion states that if we were to draw an imaginary line connecting a planet to the Sun, it will span equal areas in equal time intervals. So if the planet is at this point and it's traveling in this direction, after a given amount of time, a given time interval, say 1 month, it'll span out this amount of area. That is, the line connecting, an imaginary line connecting the Sun to the planet, will span out this amount of area. And the same amount of time, the same time interval, when the planet is on the other side of the Sun, it too will span out a given amount of area. These two areas are the same for the same time interval. This is telling us that when the planet is closer to the Sun, it's going to move faster, and when the planet is farther away from the Sun, it's going to move slower. Kepler's third law of planetary motion tells us that the farther a planet is from the Sun, the slower it will orbit the Sun, with the square of the orbital period, in other words p squared, being proportional to the cube of the semi-major axis, or a cubed. Now, if the orbital period is given in years and the semi-major axis is given in astronomical units, then Kepler's third law for the solar system can be written as p squared equals a cubed. Now, in this expression for Kepler's third law, we're not using Newton's modified version of Kepler's third law. Newton takes into account the masses of the gravitationally interacting objects. So let's take a look now at the calculation of an ellipse's eccentricity. The eccentricity E is a measure of the ellipse's elongation. The greater the eccentricity, the longer the ellipse will be. Here we have the case where we have a circle, and the circle is a special case of an ellipse with an eccentricity of 0. Here we have an increasing eccentricity, and here we have the largest eccentricity. So we're going from 0 eccentricity to increasing eccentricities. Again, the eccentricity is a measure of the ellipse's elongation. So let's look at the calculation of the ellipse's eccentricity. Here we have to define the major axis. The major axis is the long axis, and the minor axis is the short axis. Now here I've labeled A, which is half of the major axis. So A is called the semi-major axis, or half of the major axis, and B is 1/2 of the minor axis, or the semi-minor axis. The formula that we're going to be using to calculate the ellipse's eccentricity is given as the square root of 1 minus the ratio of the semi-minor axis to the semi-major axis squared. So if we were to look at the units here, we can see that from this point to this point we've got 4 units, 1, 2, 3, 4. So the major axis is 4 units long, and the semi-major axis, which is half of that, A, is only 2 units. So here we can say then that A is going to be, say, 2 units. And those units could be anything. Could be meters, could be kilometers, miles, could be astronomical units, could be light years, etc. And B, the semi-minor axis, is half of the minor axis. This is the minor axis, and this is half, and this is about 1.1 units. And notice that the units for both A and B have to be the same. And so we have that the eccentricity then, which is equal to 1 minus the ratio of B to A quantity squared, and we take the square root of that. So let's go and figure out what this is going to be. So we have the eccentricity is equal to 1 minus the ratio of B to A squared, and we take the square root of the whole thing. So if we substitute in the values, we get E is equal to 1 minus 1.1 over 2.0 quantity squared. Take the square root of that, and we get that E, the eccentricity, when you do the calculation, you get 0.84. So the eccentricity of this particular ellipse turns out to be 0.84.